Hello everybody. Welcome to another video, I guess. Um this is my PID system, or I guess you could call it aero stabilization machine. If you don't know what PID stands for, it stands for proportional integral derivative, and it's what real planes use to make sure they don't tumble over and everybody inside dies. So this is how it works. I just set it up on a smaller scale here so you can see. So yeah, proportional integral derivative, right? Proportional, what does that mean? Well, that's kind of just your simple, you take your output from your gimbal sensor and you stick it in here, right? And that increases the power, obviously, you know, using some comparator stuff, but subtract this from 15, that raises the power. Well, issue with that is it has momentum, right? You could almost say that the acceleration is proportional to the distance from equilibrium, right? The distance from zero. Well, what also has acceleration? Proportional to the distance from zero, a sine wave, right? So if you have if you just have the p, then you just have something that goes left and then right and then left and then right and then left and then right. It just oscillates back and forth, up and down forever, right? So that's not good. We can't have that. Well, the next part, and I'm going to skip the I for now. The next part is D, right? D is derivative. What's a derivative? Well, I'm not in calc, but if you don't know what a derivative is just the rate over change, right? The slope, whatever you want to call it. How fast is it changing, right? And so that's what this circuit is. So we just have the current value, right? This is the current value. We are delaying it over a long period of time, and then we're just subtracting whatever the value is now, some number of ticks later, and then we're comparing the difference, right? That's our rate of change, and then we do that on both sides, right? So this is effectively positive rate of change, and this is negative rate of change, and then we just take these, and then we're subtracting it from our proportional. So this is how much it's tilted on this side, but this is effectively our velocity, okay? So if we subtract this from this, then we kind of have an idea of how much we need to move, right? Well, that solves a lot of things, because as you can see, this has just, I mean, if I flip it over all the way, for example, and I haven't seen a PID that's been able to do this yet, so I'm very impressed with myself. It is going to take a few seconds, but you'll see, after a few seconds, it completely cancels all velocity, right? So that's what the derivative is doing. It's just seeing how much are we going to change next, and then it's outputting that and letting those values blah blah blah, right? You also have to use it. What I did is, this wasn't really enough to cancel all the acceleration, because if this is 0, well, we're not subtracting anything from 0. You can't subtract anything from 0 using a comparator. You just get 0, right? So instead, what I just did is, if that side's accelerating, which is represented by this, right? If this side is accelerating upwards, then we know to speed up this one to cancel out the acceleration. So that's our D factor, right? Our derivative. And so the last part is the I. What happens if we don't have a perfect center of mass? Now, listen, don't get me wrong. If your center of mass isn't in the middle of your craft, you're doing something wrong. If you really can't get it perfectly in the middle, then fine, but it should be your #1 priority, basically, at all costs. Okay, just get your center of mass in the middle of your craft. Alright, because, I mean, if I just get rid of this for a second, and you'll see, right? Oh. This thing can't, it's not stable anymore. I just added a bunch of weight on this side, right? Our center of mass is off a tiny bit, a tiny bit. Half a block, I'd say, at max, right? I know this thing's only 15 blocks long, so what is that? That's 30, so like 3%, right? So if you have a craft that's 50 blocks long instead, and your center of mass is a block off, then this is the amount of tilt you're going to see, right? This is massive. This is huge. What do we do about this? This is no good. Okay? Well, that's where the integral comes apart. So again, if you're not in calculus, what an integral is it's the sum of all the area under the curve, right? So if we graph the error and the equilibrium point, and we add together the area, just like we'd be calculating the area of a square or a triangle or a rectangle, if we graph the area of the curve, that's what the integral is. Well, what does this do? Well, basically, now, for a long period of time, this thing is going to lean this way. It's going to lean down, right? So we're going to get a negative integral, right? The integral is going to be saying, okay, up to this point in time, most of the curve has been below the graph. And so what this does, if I turn this back on, and I did not think that through. Well, these are, I mean, I'll just show you real quick. These are the integral values graphed out, right? So I did disable it, but it was still accumulating over time. And so as we can see, now we're on the positive side. So the integral is going from negative to positive. Obviously, it can't be both at the same time, right? But you'll see eventually, once we hit 2 or 3, that is the propulsion required from this fan for us to stay as close to the equilibrium as possible, right? Obviously, it's not going to be perfect because, again, 0 to 15, it's 4 bits. It's very rough. But they have made this amazingly difficult. I mean, accumulators perfectly calculate integrals. So all we're literally doing here is we're taking our error, okay, and then we're saying every 3 seconds, add our error, or 1, because it's too much work, add our error to our integral, right? And if we're positive, then we're going to subtract it instead, because this is obviously the negative integral. And then to prevent, like, say, 2 and 2, right, we subtract the integrals from each other. That way, if this is 2 and this is 2, so the both of the integrals are to the positive and the negative, these will just cancel them out, so they'll go to 0 and 0. And so as you can see, even though we have a massive amount of weight on this side of the craft, we are now at a relatively balanced state. We are within 3 degrees-ish, right? Obviously, it still has to react, but this is much better than earlier, where we're at, what is this, 15 degrees? Yeah, 15 degrees consistently and wavering like 6. So you can really and just to put that in, we're just 15, subtract that. That's literally it. And so, you know, again, like, please keep your center of masses in the center of your aircraft. If you're not doing that, start over, okay? It doesn't need to be perfectly symmetrical. I think you can do some stuff with, like, snow layers, maybe, if I'm not insane, where you, like, stack weight. Just try, at least. As close as possible. You can read the gimbal sensor, give it a little bit of friction. If it keeps moving even after you give it friction, then you know you have extra weight somewhere, right? And I'm not going to turn this back on because I know it's going to fly over. But we'll just isolate kind of the smaller components for you. So this is our derivative. Again, this is the same variable going in and going out. This just maps it over time, okay? So it's just getting our rate of change, and the cool part about this is comparators are constantly updating. So if this goes 5, 4, 3, 2, 1, the comparators are literally going to store 5, 4, 3, 2, 1, right? And then that updates very quickly. I tried it with inductors. Inductors are terrible. They're genuinely useless. If you're using inductors, you did something wrong. I saw a video of somebody who made a PID using only inductors and nothing else. And it was cool, I guess, but it wasn't a real PID. He was essentially just predicting how fast he think his craft would change over time, which is just so useless, honestly. And then, again, this is just our integral, right? So if we're above we'll say this is our positive integral now, right? Because obviously we have to split our positive and negative numbers into 2 variables. So if we're above the integral, or if we're above 0, basically. Okay, sorry. So, say we're below 0, right? We're going to go down, okay? And then that would transition to our negative integer, our negative integral. If we're above it, we're going to go up, right? And we're going to mass it slowly over time. That's going to cancel out any additional weight we have on one side or another. Now, I know this system isn't fantastically compact, but honestly, if you need a PID for a plane or a compact helicopter, right, you're doing something wrong as well. So, like, this is a original design I was working on where I was doing all this stuff, right? I think this is pretty reasonable, okay? I know it's quite a big area, but this is very early. It wasn't that compact. I didn't do it properly, and it's one height, right? If you can sacrifice 2 height worth of blocks, just use boards or something, then I think that's reasonable. To explain a little more on how you'd implement this, I know I have one of these components for each, but what you'd actually do is you'd have one of these for north, south, east, and west, and then you'd combine them into each propeller. So you can see with mine, I've got, my propellers aren't necessarily, I mean, where they were at least. So, like, I had a propeller here, 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 and here. They weren't on the direct north, east, south, west directions. So what you actually need to do is you need to basically calculate what is my north overall, what is my south overall, and then apply it to both of the propellers on that axis. Okay. And then I think this works for velocity too. Oh, another cool trick actually. You can turn velocity sensors on their side. So if I do that, and then boom, this is actually a very compact way, very condensed way of detecting rate of change, right? This isn't perfect because it depends on where you place it and how you set it up, and this system is just generally more variable, in my opinion. It's more versatile, and it's easier to store. But like, if you have something compact and you just need the output just straight up, then this is not a bad solution either. What else is there? Altitude PIDs are stupid. I don't know who came up with that, but that was also very dumb. Because of how air pressure works, I mean, you know, you've probably thought about this at this point, or most people have. Because of how air pressure works, right, you're naturally going to, like, if you just have max thrust, you're naturally going to approach one altitude, right? Because it's literally a sine wave, like, it's reacting for you. It's doing everything for you because the air pressure decreases as you go up. So it's just canceling the derivative automatically. The only case I can imagine you'd need that is if maybe in my case where, like, again, this thing had no additional propulsion. It was just the 4 propellers, in which case if you don't want to fall at all, then maybe you reserve some power in case you want to start moving forward, which is also, like, not smart. I mean, is it that big of a deal? Like, oh, I'm 300 blocks up and I start going forward and I'm 310 blocks. Like, you lost 10 blocks. It's not going to kill you. If that's really so important, fine, go do that, I guess. You can do this with velocity as well if you want full velocity canceling, but I think an easier solution is just using the braking mechanics of Levitite to just kill all your velocity, because this thing resists motion at slow speeds, which is pretty useful, and it's going to lift your craft up a little bit too. Do I have anything else? Steam engines are cool. Lava and dripstone, you can actually make, like, self-sufficient planes midair. Oh, right, turning. If you want to make a quadcopter like this, how I suggest you do the turning, and again, you can basically get away with no auxiliary propulsion. Like, you literally only need one, two, three, four, and that's everything you need. And we don't even have the benefit of angular momentum like drones have, right? Drones are only able to turn because of angular momentum. We don't have any of that. I've tried making angular momentum. It sadly does not work with like tires and stuff. Basically, what you want to do is if you want to turn right, so we'll say I'm sitting here. Say you want to turn right. The two propellers on this side are going to tilt forward, and the two propellers on this side are going to turn backwards. And if you want to go forward, all your propellers are just going to go tilt forward like 15, 30 degrees. And then if you want to go backward, all your propellers are just going to go backward. And that's pretty cool. So you can have like stationary gun platforms, which I think is fire, with no levitite, because levitite is lame. And anybody that uses levitite is a loser, and you're bad at the game if you do. Okay, bye.